In stats, we talked about standard deviation. So with this home run king problem, we did one var stats, and we got the mean. Well, originally, we wrote down the 5-number summary right here to make our box plot. But we also saw 2 numbers up here at the top. So up here at the top, we see the mean right here, and we see the standard deviation right here. Be really careful. If you scroll down one more spot, there's another standard deviation. We don't want that one. So in AP Stats, we are using S. We are using 12.6865 for this data set. Notice down here it's a touch, just barely different, and that's usually the case. So there's our mean, there's our standard deviation. So let's go back to the problem and write those 2 things down. If you haven't yet, you probably have a box plot down there. Let's actually go to the standard deviation page. Here we are. So we have a little bit of information about standard deviation. Down here it says to find the standard deviation of the home run for the home run king problem, and you already know it. It was revealed in one var stats. So that is the sample standard deviation. But let's back up and let's talk about it. So at the very top of the screen, you see some monstrous formulas. It gives you an interpretation of standard deviation. It is, if you want to write this down in words, standard deviation is the average distance a value is from the mean. And what they do whenever they start out is they get a deviation, or whoever is doing the calculation. They get a deviation. So for example, in the home run problem, if you're looking at it right now, let's flip over to it. We have all his home runs. Now you maybe don't have room for this on this page, but on that standard deviation page, the mean is 360476, and each observation represents number of home runs. Those are our X's. So we start by writing, say, 25, 24, 19, all the way down to the last season when he had 16 home runs. And when you add up all those home runs, you get the sum of the X's, which is right there, 757. The sum of the X's, it's not very helpful in this circumstance. So the next thing that one might think would be useful is to do the deviation. So if you just write that right there, that's deviation from the mean. And the calculator doesn't give that value, I believe. You could calculate it pretty easily. You just go 25, that's X, minus the mean. You would have to do this 21 times to get each deviation. This one is negative 11.0476. So that's the first deviation. 24, it's a touch further away from the mean. It's going to be negative 12.0476. And something interesting happens when you get all the deviations. This is, if you understand what a mean is, what an average is, then you can guess what this total at the very bottom will be. Because what it's doing is it's getting all the distances from the mean. In a way, it's kind of like undoing that summation for the mean. So when you add up all these deviations, you get 0. Some of the deviations are below, and they're negative. Some of the deviations are above. So, for example, I see a 46 in there. That one's above. That one is, what is that? 10.0476. And when you add them all up, it's like undoing the average, and it's 0. So those deviations are actually of no use to us. So what a clever statistician did was they took each deviation and they squared them all. And now we have positive numbers. So every single squared deviation should be a positive number. And when you add them up, down here, you have the sum of the squared deviations, which is the numerator for what we call the variance. So go back to the problem. Let's make a big screen here. And this right here is called the sample variance. They do exactly what I just described. See, they're squaring each deviation. They add them all up, and they divide by not n, but n minus 1. They divide by n minus 1 so that they can avoid bias. If you don't divide by n minus 1, it tends to underestimate the true value, the population value, so they divide by n minus 1. There's an actual bias formula that you can do, and if you don't divide by n minus 1, there's value in bias, and you don't want bias. You want bias to be 0, so that's why they divide by n minus 1. So that's the sample variance. That's like the squared deviations, like average deviations. So squared, that doesn't really help us, so that's why we square root sample standard deviation. You square root the variance. All right? So in the home run problem, they end up getting 12.6865. This is on average the home runs Barry Bonds hits is 12.6865 home runs. That's redundant. I already said home runs up there. Away from the mean. You can use the word mean, you can use the actual mean and write, 360476. But on average, the home runs Barry Bonds hits each season is 12.68 away from the mean. It's not a sure thing. Sometimes it's less, sometimes it's more, but it's on average 12 home runs away from the mean. And a big reason for that was 73. One season he hit 73. That pulled the standard deviation higher, which is what this down here is talking about. If we have a an observation that is really far from the mean, that's going to have an effect on the standard deviation. Remember, we're squaring them all. That's why it's always positive. It could never be negative. If you're doing multiple choice and there's a negative choice, that one's wrong. Cross it out. If for some reason standard deviation is 0, that means there is no variability. All right? They love when you talk about variability. Most data sets, 99% of them, have variability. Therefore, they have a standard deviation. Last thing, units are the same as what you measured for each observation. So for standard deviation for Barry Bonds, it's 12.6865 home runs. All right? Last thing we did, we walked through all the statistics that we calculated, and we wrote yes or no to this question. Do outliers affect? And we answered it. So maybe hit pause and see if you know. Yes, outliers do have an effect on the mean. No, not the median. Yes to range. No to IQR. And yes to standard deviation. Ask yourself, for which of these stats are you using all the data or the ends of the data? And for median, that's just the middle number. Outliers have no effect on it. For IQR, that's Q1 and Q3. Outliers are not at Q1 and Q3. That's impossible. But the three others, yeah, you use min and max, any large value, the entire data set. Outliers do affect those. And that was all we did today. I'll see you later. Bye.